Hello, this is Jack Jackson. In this video, we're going to talk about trigonometric functions just a little bit and using calculus and precalculus to analyze their graphs. So the first thing you need to remember when working with trigonometric functions in calculus is to always put your calculator in radian mode. So be sure that you do that first, okay? Always the input is in radians in calculus. Or at least almost always. So like rational functions, the 6 basic trigonometric functions are differentiable where they are defined. Now the sine and cosine functions are defined everywhere, but tangent, cotangent, secant, and cosecant all have infinitely many places where they are undefined, and they all have vertical asymptotes at these places. They do not have holes in the graphs, but they do have places where they're undefined and they have vertical asymptotes there. Now, unlike the rational functions, the basic trigonometric functions are periodic. In fact, unlike all of the functions we basically study in basic algebra classes, the trigonometric functions have this characteristic that they're periodic. In fact, that's one of the main reasons why we study trigonometric functions, is we like to use them to model things that are periodic. In other words, things that go in cycles. Cycles are waves. We use trig functions to analyze them. So if the function has one x-intercept, then it has infinitely many x-intercepts. If the function has one local extrema, then it's infinitely many local extrema. If it has one vertical asymptote, then it has infinitely many vertical asymptotes, and so forth. So when we analyze trigonometric functions, we must be sure to illustrate this periodic behavior and to clearly identify all of these infinitely many places where these things happen, not just one or two of them. Now, we're going to be using a lot of skills from precalculus in this video, and calculus as well. Certainly some algebra skills, actually several algebra skills, and we're also going to be using a lot of trigonometric skills. So if you need to review the graphs of the basic trig functions and some of their basic characteristics, then I refer you to some of my other playlists. Okay, so for example, I have a playlist called Trigonometry Unit 2, Circular Trigonometry, which introduces the definitions of the circular trigonometric functions and visualizes these both on a unit circle and Cartesian graphs. So for example, we define the sine of x in terms of a circle centered at the origin and points on there, and we can also wvisualize that as a wave shaped graph on a Cartesian graph. And there are also videos going over trigonometric values for certain special angles, and all of those basic characteristics are going to kind of show up in this particular analysis that we're getting ready to do. We also have we're also going to have to solve some trigonometric equations in this analysis that we're getting ready to do. And my playlist on Trigonometry Unit 4, Identities, Equations, and Inverses, gives some examples of solving equations such as the ones here, and it sort of builds that up a little more slowly than I'm going to have a chance to do here. Now, there are going to be many details to this problem. This is going to be kind of an involved problem, so kind of bear with me here. Okay? But it has details that are going to include finding a first and second derivative, solving some polynomial and trigonometric equations. We're going to use the quadratic formula. We're going to use some special triangles and trigonometric functions of some special angles. We're going to use even approximation techniques of zeros using the sort of built-in version of Newton's method in your calculator with the Calc 0 or Calc Max or Calc Min for finding some extrema. And we'll use some other algebraic, numerical, and graphical techniques. So we're going to kind of be using lots of stuff here, and this is a good example for us to work on to help, among other things, just review some of these details. So here's the function that we want to look at. F of x equals 2 sine cubed of 3x minus sine squared of 3x minus 2 sine of 3x plus 1. Now notice you can think of this as composing things. We start by taking the x and multiplying by 3 in each case. So they take that linear function 3x, and then we apply the sine function to that, and then we take sine of 3x and plug it into a polynomial function, and we get this. Now, since all of those things, linear function, sine function, polynomial function, those all have domain all reals, and they're actually differentiable in all reals. So we know that this function is going to be differentiable everywhere. We should be able to find a derivative for it, and using our derivative shortcut rules, and we should be able to know that that derivative is defined for all real numbers. So we'll get that. So among other things, that tells us that the graph is a continuous function, so it's a continuous graph, one connected piece, and it's actually smooth as well. Differentiable is going to imply smooth, so there are no sharp corners, no holes in the graphs, no vertical asymptotes, no breaks of any kind. Okay, so notice if we do a substitution where u is sine of 3x, this becomes 2u cubed minus u squared minus 2u plus 1. So there's your polynomial function I was just talking about. Now notice that sine of x is periodic with period 2 pi, and u equals sine of 3x is periodic with the period of 2 pi divided by this coefficient 3, so 2 pi over 3. So notice, think about it just a minute. If the input 3x goes between 0 and 2 pi is one period, so we have 0 less than 3x is less than 2 pi, divide everything by 3, and then we've got 0 less than x less than 2 pi over 3. So when x goes from 0 to 2 pi over 3, 3x goes from 0 to 2 pi, and you'll get one full period. So we'll get one full period from 0 to 2 pi over 3, or any interval that's of length 2 pi over 3 will be one period. So f is going to have that same period as well. The polynomial function is not periodic, so that's going to. So we should get that same thing. We'll see if that works out. So if we graph the function, say from 0 to 2 pi over 3, then the rest of the graph is just infinitely many more copies of that shifted around horizontally. So if we summarize what we have so far, the domain is all real numbers. We know it's continuous at all reals. It's actually infinitely differentiable. First derivative, second derivative, third derivative, fourth derivative, etc. all exist. And the period is 2 pi over 3. So let's graph it. This is a graph using Graphmatica, and it's on a square scale. And the vertical line spacing, they're spaced apart at pi over 18. And you can see from 0 to, well, 2 pi is about, well, right here, where y equals 1 hits the graph, right here to here. So that's one period right in this part right here. And notice you get the same thing over and over and over and over and over again. So this thing is periodic. Also notice that if we take the limits as you go to infinity or minus infinity, they just don't exist. It's not getting closer and closer to any particular value. In fact, it keeps oscillating between whatever this lowest one here and whatever this highest one here is. So it has some global maximum and some global minimum, and the range is between those two. So now let's kind of focus in here a little bit. So let's just say on one period, it looks like we've got 4 x-intercepts, those red dots. Actually 3 minima, the 2 green ones are absolute minima and local minima, and this one red dot looks like it's a minimum and an x-intercept. And it looks like we got a maximum at this red dot right here, which is also an x-intercept, but then there are 2 global maxima up here. So it looks like on any one period, we're going to have 3 maxima, 3 minima, and 4 roots, and there's going to be several inflection points too. One right in here, one in here, 2, 3, 4, 5, 6. Looks like 6 inflection points in there. All right, let's see if we can find some of the actual values of some of those. Okay, so to find the roots, the x-coordinates of those red dots, we need to set the function equal to 0. So that is 2 sine cubed of 3x minus sine squared of 3x minus 2 sine of 3x plus 1. And I'm going to let u be sine of 3x. I can rewrite that as 2u cubed minus u squared minus 2u plus 1 equals 0. It's not absolutely necessary that you do that, but it's a lot easier for me to see what's going on if I just deal with u's, and then I'll switch back to x's, or maybe even thetas first and then the x's. So there's my polynomial function. How could I find that? Well, that should have potentially up to 3 factors, okay, 3 linear factors. But maybe it's not quite so obvious. If you know the rational root theorem, you might have a list of the possible rational roots that you could try. It's not too big in this case. So you might just kind of trial and error try those. But we can also have graphing technology. So I'm going to take the graph and plug this in as y1, or if I already have the original in as y1, put this as y2, turn off the other one. But anyway, I put the graph in where instead of a u, I've got an x. And in this case, from -3 to 3 for x and -1 to 2 works pretty nicely. I can see this, and I'm interested in what these x values are where it crosses. Now, these x values actually are the u values up here, not the original x's. Okay? And if we calculate those, say calculate 0, and of course you have to give it a left bound, a right bound, and a guess. And so it's doing Newton's method internally. And it's going to come up with -1, 0, 1/2, 0, and 1, 0. And of course, if we check this, we see that, yeah, those are the places where y is 0 at -1, 1/2, and 1. And so that says that the factor should be x minus these roots. So x minus a -1, or in other words, x plus 1, and then x minus 1/2, x minus 1, and we still got our leading coefficient of 2. And so we can see that factorization right there. Just to double check that, I can put that in as y2 and check that these two are equal, and sure enough they are. So it's a little polynomial analysis right there first as a step along our way. Alright, so therefore we've got f of x, which was this guy, equal to 0, is when this expression in terms of u, this polynomial, is equal to 0, which factors like this. Now remember, u is sine of 3x. In a minute, I'm going to let 3x be theta, and so we know that sine of theta is also u. We'll get to that in a minute. Alright, so now, if this is equal to 0, we have a property of 0 that says if you have things multiplied together to equal 0, one of the factors has to be 0. Of course, 2 is not 0, so one of these three has to be 0. U plus 1 equals 0, so that says u is -1. Or u minus 1/2 is 0, says u equals 1/2. Or u plus 1 equals 0, which says u equals -1. But now wait, u is sine of theta, so I have sine of theta equals -1, or sine of theta equals 1/2, or sine of theta equals -1. Now see if we can come up with values for these here, and in fact, we can come up with exact values for these without having to use an inverse sine function or an arc sine function, because these are special angles. And we can actually look at these special angles. Many of the problems in the calculus textbook and the trigonometry textbooks end up using some of these special angles and these special values. So let's look at the first one. Sine of theta equals -1. So sine of theta equals -1. Let's see if I can kind of get all this on one page here for you. Close. There we go. So sine of theta equals -1. You can think of that as -1 over 1. Now remember, on a circle picture where we have a circle centered at the origin of radius r, the sine of theta is y over r when your angle is in standard position. So let me just remind you about how we define the sine function. So we take a function of radius r, we take our initial ray, which is going along the positive x-axis. If you see this, see my cursor moving down here in the picture. And then you spin it, and it ends up somewhere else. Okay? So in this particular case, it's actually going to end up straight down. Okay? And then you take where that ray, where it ends up, that's called the terminal ray. Your initial ray's over here, and there's your angle. And that's we find out where it's going to cross the circle. That circle has now, there's actually 4 numbers related to that. One is the amount of the angle, so that takes the point 0, 1, or 1, 0, and traces it along a path here, and you measure that arc length with like a tape measure. That's how we measure the radiant angle. So that's the input for theta. So theta is going from here, or which would be positive. In this case, it's all the way around is 2 pi. So this is actually a quarter pi, half pi here is a quarter circle. So half a pi, pi, 3 pi over 2. So 3 pi over 2. Or we can go in the other direction, which would be the shortest amount of rotation, and that would be a negative angle, negative pi over 2, gets you to there. So it has a theta that's associated with it. It also has an x and a y, and then an r value. And sine of that angle, sine of that theta value, is the y value of that point, this point right here, in this case 0, negative 1, over r. Now, it's the easiest to put this in the unit circle in this case, which has radius 1, so r is 1, y is negative 1, so you think of this as y over r, negative 1 over 1. So we've put this inside a unit circle, and we see that means this is pointing straight down. We know one way to get there is to rotate negative pi over 2. Or we could rotate by 3 pi over 2 if we go this way. So I'm going to use 3 pi over 2. I can use any one. There are actually infinitely many angles, though, that end up there. Not just negative pi over 2 and not 3 pi over 2, but, for example, instead of 3 pi over 2, I could rotate all the way around 2 pi, and then another 3 pi over 2. Or rotate around 3 pi over 2, and then another 4 pi, another 2 full circles. It only matters where that thing ends up. So, in fact, our input could be any real number there. And get an angle out. The ones, though, that point straight down, only one terminal side is allowed to get this particular value for the sine. So all those angles would end up the same place. And so we can express that as 3 pi over 2 plus 2n pi such that n is an element of the integer. So let's look at these symbols, make sure you know what this means. So theta is our input angle, which is our arc length here. That symbol means is an element of. The curly braces mean a set. This is 3 pi over 2 is one of those angles, and then we add to that some n times 2 pi. The vertical line is such that n is an element of, and that funny looking z is for Zahlen, which is German for the integers. So that's typically the symbol that we use for integers is z. Of course, integers are 0, 1, negative 1, 2, negative 2, 3, negative 3, 4, negative 4, etc. So what we're doing is we're adding or subtracting complete rotations, full circle rotations to our 3 pi over 2. Now similarly, if sine of theta equals 1, you can think that as 1 over 1, which is y over r, and that means it goes through, you need a circle of radius 1, which is this black circle here, and we want to find where y is 1 on that circle when there's only one place, it's right here, and so the terminal side must be pointing straight up. One way to get there is pi over 2, but another way is to get pi over 2 plus 2n pi for any n where n is an integer. And then here's the graphic for that. Now, so notice we have infinitely many solutions to this first equation, which are theta is 3 pi over 2 plus 2n pi. One terminal side, but infinitely many thetas. We also have only one terminal side for the middle part. Theta is pi over 2 plus, but infinitely many angles. Theta equals pi over 2 plus 2n pi. For the middle solution. Now about the third, that's the last one, excuse me. Now what about the middle solution? There's some typos there. Let's see if I can fix that. One of those is supposed to be. Okay, there we go. Now I fixed it. One of this is supposed to be u plus 1. One is u minus 1. The u minus 1 gives us u is positive 1. Sine theta is 1. So this last part is the second part I did here. First part I did here is the first part. Now we still got to take care of this middle part. Okay. So sine of theta equals 1/2. Well, again, think of sine of theta as y over r. The easiest way to think of that, I think, is to think of it as 1 over 2 is y over r, so y is 1, r is 2. So we're going to think of this in putting this in a circle of radius 2. Here's the picture down here, circle radius 2, and we want a y of 1. So it's halfway to the top. This is 2. So if you go halfway to the top, it's right here. So it's either there's 2 places. I've got 4 things here. I also got where y is negative 1. So ignore these down here in quadrant 3 and 4. The ones we need are either in quadrant 1 or quadrant 2. And this is the terminal side, either here or here. Of course, the initial ray is along the positive part of the x-axis. And there's your angle. Now, what does that mean? We have what we call a reference triangle, which you take this point where it crosses and come down. Notice that the hypotenuse is 2 and the vertical side is 1. And by using the Pythagorean theorem, we can see that the other side is square root of 3. Now, what we notice is that this is actually half of an equilateral triangle. If we go on down here, now you can see the whole triangle here. And we see that this vertical side now, the big triangle, is 2, and that's 2, and that's 2. So each of these angles is just, of course, the sum of the angles in any triangle is pi radians, or 180 degrees. And you divide that by three equal parts. Each of these angles here, this one here, and this one up here is pi over 3, and this big one's pi over 3 here. But what we have for our reference angle is half of that, which is pi over 6. And so this is a special triangle that you're going to see used quite a bit. Okay, and it's got a congruent version of it over here in this quadrant, in the second quadrant. So what does that mean you have for your coordinates for x, y, and r? Up here, r is 2, x is square root of 3, and y is 1. And the angle, the reference angle, one way to get there is pi over 6. Now how about this one over in this quadrant? Well, x is negative square root of 3, y is 1, r is 2. And of course, by the way, once you get that, you can find all 6 trig functions like I've done here in the picture. Now, what we can also do is say, well, what is that angle? Well, this angle, again, is pi over 6, the reference angle, but it's pi all the way to here. So it's pi minus pi over 6. Okay, pi is 6 pi over 6 minus 1 pi over 6 is 5 pi over 6. So 5 pi over 6 will be the rotation that starts here and takes you to here. Okay, so all the rotations are 5 pi over 6 plus 2n pi. Those will be the ones that end up with this terminal side here. But the terminal side in the first quadrant are pi over 6 plus 2n pi. So they're actually two different terminal sides that give you a sign of 1/2, positive 1/2. But each one of those makes a whole infinite set. So when put it together, all 4 of these solutions, 4 sets of solutions, there's one here that's rotated, a rotation for theta that goes straight down. This one goes straight up. This one goes in the first quadrant this much. And this one ends up in the other quadrant over here. So you got those 4 different rotational angles, and you put them all together. So where does theta have to be? It's pi over 6 plus 2n pi, or pi over 2 plus 2n pi, or 5 pi over 6 plus 2n pi, or 3 pi over 2 plus 2n pi, again, such that n is an integer. Now, instead of 3 pi over 2, I could have used anything that gave us the same same terminal side. So instead, I could replace the 3 pi over 2 by minus pi over 2 if I want. Then you just choose a different value to n to get the different angles. Now, this is a solution to this trigonometric equation right here, this part right here, but wait a minute. We didn't ask what theta is, we want to know what x is. Now remember, theta is 3x. So here we have theta as an element of this set, so it says 3x is an element of that same set. Well, if each one of these is equal to 3x, to get x, you just divide each of these by 3, and we have to distribute. So pi over 6 divided by 3, or times 1/3, is pi over 18. And I'm going to write this as n times 2 pi over 3. And I'm going to write this one as n times 2 pi over 3, each one of these. And then this here, pi over 2 times 1/3 is pi over 6. 5 pi over 6 times 1/3 is 5 pi over 18. 3 pi over 2 times 1/3 is just pi over 2. And these are the possibilities that make f of x 0. So there are infinitely many x-intercepts, and of course these are the x-coordinates, the y-coordinates are 0. So here's the same set of x's stuck in ordered pairs with y being 0. And so you got these 4 infinite sets here. So in any period, you're going to get one of each of these here. in a particular period. Pick a different value for n, and then you've got a different period going on. Now, if you want to know decimals, approximately what these are, I've worked these out here. You can see I've worked them out on the calculator. Pi divided by 18 is 0.1745, etc., and so forth. So I've worked out all of those, and then even 2 pi over 3, I even worked out what that is. It's about 2.0944. So there's 4 decimal place approximations there, and the actual real things are what's in the box right here. Now, of course, being a function, there's exactly one y-intercept. That's when x is 0, so plug that in. 3 times 0 is 0. Sine of 0 is 0. And so you see the only thing that remains standing here is just 1 at the end. So 0, 1 is the y-intercept. Now, so if I were to graph this, I got the graph down here below. Okay, so here's a graph of one period. So these red points right here are those x-intercepts that we just found. So this first one is going to be the smallest of these 4 numbers. Which one's smallest? The 0.1. So that's the pi over 18 is the smallest. And then the next, I think I have them in order. Pi over 6 is the next one. So this is pi over 18, 0. This is pi over 6, 0. This one is pi over 5 pi over 18. And then the last one is pi over 2. Those are all integer multiples of pi over 18, so that's why I've got this graphed out with the vertical lines at pi over 18. Okay. Actually, that's not true. I've got it graphed out. The first one actually is pi over 18, which is 2 grid lines. So actually, they're spaced out at pi over 36. Started out with a pi over 18 and decided to cut it in half. Okay, and I think this I have the same spacing up here on this graph that we looked at earlier. Okay, keep going here. All right, now let's look at this picture here again. This is from 0 to 3 pi over 2 pi over 3. Excuse me. Now, within one period, it looks like we have some extrema here. Now, it looks like this is going to be a maximum as well as an x-intercept for this one, and a minimum as well as an x-intercept for this one right here. But we have 2 other minima and 2 other maxima. And it looks like from the picture that the y values are tied here for its global max at the orange dots and global min at the green dots. So let's see if we can find those guys. So how do we find a maximum or minimum? Well, we take the derivative and set it equal to 0. So here we go. Let's find a derivative. So again, it's going to be easier, I think, if we do a substitution. So we're going to be using the chain rule here. So let u be sine of 3x, or in other words, sine of theta, same as we did before. And so this is 2u cubed minus u squared minus 2u plus 1. We're going to do a derivative. Now, in a minute, we're going to need du. So du over dx is, well, it's the derivative of sine theta, which is cosine theta d theta, which is derivative of theta with respect to x is theta is 3x. Okay. And since theta is 3x, then the derivative of theta is just 3. Okay. And we'll need that. And so then this derivative is 3 cosine of theta. Okay, we can get it in terms of x later, but I'm just going to write it like that. All right. Now, what do we have here? So this, doing our derivatives, this is 6u squared, but then it's times du over dx, minus 2u du over dx, minus 2 du over dx plus 0. They all have a du over dx, so I can factor that out. In fact, I can factor a 2 out as well. So that leaves 3u squared minus u minus 1, a 2, and a du over dx. Du over dx, again, is 3 cosine theta. So this is 6 cosine theta, 3u squared minus u minus 1. And, of course, if I put this all the way back to the beginning, put everything back in terms of x's, cosine of theta becomes cosine 3x. Each one of these u's becomes a sine of 3x. So here's the actual derivative as a function of x. But I'm actually going to use this version here with some thetas and u's in it. So when the derivative is 0, that says, well, the 6 can't be 0. So either cosine of theta equals 0, or this 3u squared minus u minus 1 equals 0. Now, you know, a lot of times you work with problems and they factor very nicely. You know, like when we were looking for the roots, I sort of contrived this thing. So we got some really nice factoring going on here. And we even got numbers that gave us special rotational angles that we could use things like our special triangles here, half a equilateral triangle, and stick in there. Now, the more realistic situation, however, is what we have here, is that you get a quadratic equation and you can't find a factoring for it using integers and rational numbers. Well, luckily we know the quadratic formula, so we can find this using the quadratic formula. Quadratic formula says it's the opposite of b. So if you got a u squared minus plus bu plus c equals 0, it's the opposite of b plus or minus square root of b squared minus 4 times a times c over 2a. See one of my algebra videos for how to derive that formula and using it quite a bit, but hopefully you remember that. That's pretty commonly used. So these two negatives make a positive 1. Negative 1 squared is 1. 2 negatives make a positive here. 4 times 3 is 12 times 1 is 12, plus that 1 is 13. So I got 1 plus or minus square root of 13 over 6, which is u. But u is the sine of theta. So here I have cosine of theta equals 0, or sine of theta is 1 minus the square root of 13 over 6, or sine of theta is 1 plus the square root of 13 over 6. Alright, now what's theta? Well, this one, cosine theta equals 0, is one of our basic ones. So if we go back to, say, this unit circle picture, we want to find cosine theta. Remember, cosine theta is x over r. R is 1, so x is the cosine of theta here. So when is x equal to 0? That's when it's pointing straight up or straight down, either one. So pi over 2 or 3 pi over 2. Okay, so it's either pi over 2 plus 2n pi or 3 pi over 2 plus 2n pi. So that's the n as an integer. That'll get the first part. Or we get this one. Now, for sine, first of all, 1 minus the square root of 13, when you're doing this, we can do the arc sine of this, the inverse sine, but that's only one of the two possibilities. For example, I know 1 plus the square root of 13 over 6 is a positive value, so that's going to be, the sign is positive. This will be in the first quadrant when you think about theta, or be in the first or second quadrant. But then there's also one, let's say if it's in the first quadrant, then there'll also be one in the second quadrant also with the same y value. Okay? So in that case, you could also, and they're actually supplementary angles for each other. So you have to be careful when you have sine of theta equals something, because you can solve for theta by doing an arc sine or inverse sine of that something. But then you can also get pi minus that arc sine. And of course, you can also get, once you find one of those guys, one of those angles that gives you a terminal side in the right place, you can also add any integer multiple 2 pi to that as well. So there are two infinite sets of angles that give you this last one here. For example, arc sine of, here it's down here, arc sine of 1 plus the square root of 13 over 6 plus 2n pi, or pi minus arc sine of 1 plus the square root of 13 over 6. Okay, let me see, I had a saw typo there, let me fix it real fast. right there. Okay. So plus and plus there. Okay, or you could have it with a minus there and there. Okay, and works kind of the same way. So we put all that together. It's all, any of those. So you union those together. So what do we have? We have pi over 2 plus 2n pi, 3 pi over 2 plus 2n pi. The arc sine of 1 minus the square root of 13 over 6 plus 2n pi. Pi minus the arc sine of 1 minus the square root of 13 over 6 plus 2n pi. The arc sine of 1 plus the square root of 13 over 6 plus 2n pi. Pi minus the arc sine of 1 plus the square root of 13 over 6 plus 2n pi. Now, maybe when you're doing a lot of trig equations in trigonometry, a lot of times they worked out like the ones in the roots that appear, where they worked out to be one of these special angles, so there were no arc sines in our final answer because we could work these out exactly. Things like pi over 6 and pi over 2 and so forth. We could work those out. But in a way, those problems are somewhat contrived because the more realistic situation is something like this. There are very few angles that we can actually get rid of the arc sine on very easily. Okay. Now remember, that's theta, however. So theta is 3x. So to get x, I need to divide by 3. So dividing these by 3 and distributing, I get pi over 6 plus multiples of 2 pi over 3, pi over 2 plus multiples of 2 pi over 3, 1/3 arc sine of 1 minus square root of 13 over 6 plus multiples of 2 pi over 3, pi over 3 minus 1/3 arc sine of 1 minus square root of 13 over 6 plus 2 pi over 3 times n, and so forth. You can read across there. So you got 1, 2, 3, 4, 5, 6 infinite sets of these things. So 6 basic ones within one period, and then shifts of those by the period. Okay, and here you can see some decimal approximations for those. On these decimal approximations, I used n equals 0 on all of these except for one, because because any of these that you plug in as 0, they give you something between 0 and 2 pi over 3, except for one of them gave me something negative. And I can't remember which one it is. I think it's this. Well, I say later. The 1.9447. Yeah, this first orange one. If you plug in 0 here, the arc sine of 1 minus the square root of 13 over 6 times 1/3, I think, is a negative. And so I wanted to. So in this case, I let n be 1. So this 1.9447 is where the n is 1 up here, and so n is 1 here corresponds to n equals 0 here, but all the others, the n's are the same. Alright, well anyway, you can see I got the decimal approximations by typing some stuff in my calculator. You can pause that and read those if you want. Now again, if we look up close here, we're going to see a total of 6 extrema. 1, 2, 3, 4, 5, 6. Okay, now these two red ones here we already encountered at pi over 2, I believe was this one right here, and this one was at pi over 6. Okay, so the one at pi over 6 is a maximum, this one's a minimum. Now how do you know which one's a minimum or maximum? Well, we have a couple ways to do that. We can look at the values of the second derivative. See, the second derivative is positive here, it's concave up. So this first one right here is going to be a minimum. Okay, you could also just look at this graph. Probably the easiest way to do it. Once we get a fairly decent looking graph, we can just tell by look at it and say, well, that's definitely a minimum, not a maximum. And this is a maximum, not a minimum, and so forth. Now there is the possibility if the second derivative was also 0, that it would be an inflection point possibly, and not a max or min, but in fact all 6 of these sets are in fact extrema. Half of them are minima and half are maxima. And so if you look at it, the 2 green ones are minima, and as well as the this red one here at pi over 2, and the 2 orange ones are maxima. So the 2 orange ones are actually global maxima, and the 2 green ones are global minima, and this red one right here and this one right here are local maximum and minimum respectively. And so I did for the ones in, just the ones only from 0 to 2 pi over 3, here are decimal approximations for them. And they're the ones that you can see on this graph. But remember, this is not all of them. In fact, they're horizontal shifts of this by any multiple of 2 pi over 3. And so you see the full set is actually given here of the x values. Now, if you want to find the y values, all of these, actually both of these orange ones and any shifts of them have the same y value, horizontal shifts. And these two green ones have the same value. The red ones all have y value 0. Okay, and you see at least decimal approximations for what those are here. And you can check those with Calc Max and Calc 0. So the x-intercepts, I can check those by doing Calc 0 here, here, and here, and here. I missed one. There's one there. I should have checked it as well. And that's going to, you can check to see that all those work out. Then the 3 minima and the 3 maxima, you can see I've checked those here with the calculator, and that checks out as well. Now here's the actual full list. And I've kind of color-coded it so you can look at the picture above. But it's pi over 2 plus 2 pi over 3 times n, comma 0 is a minimum. Okay, that's that guy and all shifts of it by multiples of 2 pi over 3. And then here is here's the exact values for that one. Now all I did here, I didn't even simplify it because I don't know, there's no way to really simplify it. I just took the 1/3 arc sine of 1 plus square root of 13 over 6 plus 2 pi over 3n. And we could let n be 0, so we could let that go away. But we could take this part right here and plug that in for x in the original 1. And notice that I've got it right here where there was. So 2 sine cubed of x. Oh, that's not right. This needs to be 3x. So the 1/3 are going to go away. So let me fix that. Let me fix that problem. So this should be actually 3x. So that's going to make these 1/3. Oh, wait a minute. We might be able to simplify this now that we don't have the 1/3. Okay, let me do a little simplifying here. Okay, now what does this say? This says you take the angle whose sine is this, and then you take the sine of that. Well, the sine of the angle whose sine is this angle. So what this really works out to be is just this sine and this arc sine cancel. And what we end up with is this cubed. And here we get the same thing squared. And here we get just this part like that. Okay. For the y part here. Let me put a little space there. Okay, and this, you get the similar thing here. It's exactly the same thing, but with down here, it's the same thing here. Except these are minuses right here. Okay, now we could do a little more algebra and actually simplify this. We could actually simplify this down quite a bit as well. Okay. Okay, so let's copy that. Okay. You know what? I don't want to do this right now on this. On the notes, I will go ahead and work out the details of this. But what we're going to end up doing is using, we'll square the denominator here. We'll use FOIL, square out the top, and we'll have to take that, square it, and then multiply by another 1 plus square root of 13 distributive property. We'll have the 6 cubed there. Okay, so anyway, this will all expand out, get a big common denominator all the way across, including the 1 here, and eventually you can get this all simplified down. It's probably still going to have a square root of 13 in it somewhere, but we can simplify this down into one single expression. So a lot more algebra, well, not really algebra, it's really arithmetic at this point, but to work that out. And but it's arithmetic with some irrational numbers there. So I'm going to not do that in the video, but here are the approximations down here. Okay, so remember it was sine of 3x, so I took this x here, multiply, I let n be 0 because it doesn't matter which one it is, they all have the same y, multiply by 3, the 1/3 cancels, and then I have the sine of the arc sine, just gives me the part that's inside, they cancel each other out. So we get a similar kind of situation going over here for these others. Okay? Now here's a graph of the original function in blue and the derivative in red, and I've got, looks like 2 periods from minus 2 power over 3 to 2 power over 3. And notice, of course, that like you always see with the derivative, when the derivative is negative in here, from here to here, we have this, from this maximum to this minimum right here, the original function is decreasing. And then it increases from here to here. That's from when the derivative is positive from this x-intercept to this x-intercept on the derivative. That's going to be from this minimum to this maximum. And then the derivative is negative again, so it's going to decrease. The original function is decreasing. And then the derivative goes positive for a while, and it's going to increase back up to that maximum. And that's one whole period from that maximum to the maximum here again. Okay? And so just as the original function is periodic, the derivative is also periodic. Now, what about let's see here. What about this? Where are the inflection points? Okay. Well, to do that, we need to find the second derivative. So here are the substitutions we made. Later on, I want to use this identity that cosine square theta equals 1 minus sine square theta. So with our substitution, cosine square theta is 1 minus u square. Okay. So theta is 3x, so d theta over dx is 3. And we have these derivatives. Here's the original function and the first derivative. So the second derivative, I can look at it in this form right here. That's a constant multiple rule, says I can just put the 6 out front. I got this big bracket here. Now I use the product rule, that's the first times the derivative of the second, so let's derivative of this polynomial, plus the second, the polynomial times the derivative of the first. Okay, let's do the easy part first. The derivative of cosine theta is the opposite of sine theta. Be sure you put parentheses or else that means subtraction, and it's not, it's multiplication by negative. And then times the derivative of theta. Derivative of theta is 3, so we have that. Now over here, the derivative of this polynomial is 6u du over dx minus 1 du over dx plus 0, and I factored out the du over dx. So I'll just left that 6u minus 1 for the moment, but du over dx we already worked out was 3 cosine theta. Alright, now let's see if I can work with this just a little bit. What have I done here? Didn't look like I did anything on that line. Probably just take that line out if I'm not going to do anything. Just an extra copy. Okay, so what do we do next? Okay, so I did a little factoring. First I pulled the 3, this has a 3 and this has a 3. Pull that all the way out front with the 6 and make it an 18. Then I wrote cosine square as 1 minus u square. This is cosine square because you got a cosine here and a times a cosine here is a cosine square. So that's 1 minus u square. This is 6u minus 1. Sine is u. Sine of theta is u. So I've got a minus u times this polynomial, the 3 I factored out front here and here. Now I use FOIL here. and you get this, these four terms. Distribute the minus u here, so you get all of those terms. Pause that if you need to think about it a minute. Okay. Combine like terms and put it in decreasing order here, and I factored out a -1 here. So now I have this polynomial. But now I substitute back in u as sine of u as sine of theta, so I wrote it back like this. And in fact, I could even go a bit further, of course, is go all the way back to x's, and theta is actually, of course, 3x. And here's the second derivative back in terms of the original variable x. Now, when is the second derivative 0? Well, you're going to need to put this polynomial equal to 0. That's a cubic polynomial. There is a cubic formula, but it's typically not taught in precalculus, so you probably don't know a way to do this exactly. So now at some point here we're down to doing approximate solutions. So we'll come back and do this, look at this a different way. So what can we do? We can either graph this right here, this version of the second derivative, and calculate the zeros using, say, Newton's method approximately, or just the calc 0 on the calculator, or we could get equivalently the same thing by finding these. Notice, well, here's the second derivative in green, and the first derivative is in red. Notice that, as always, the second derivative crosses the x-axis and goes through the other side exactly when the red one, which is the derivative, has either a maximum or minimum. So instead of calculating the places where the second derivative is 0, since we have a built-in maximum finder, approximator on our calculator, we can do a calc max and similarly a calc min. So what we're wanting to find is the x-coordinates of of these places where the derivative is at a maximum or a minimum, and then we want to find the original y's of those. So notice in y1 I've got the original function, y2 is the derivative, and I've got a window here that goes from 0 to 2 pi over 3, so I'm just looking at the first period here, one period of it, and so I need to find the coordinates. So I'm looking here, the first one I'm finding, there's a minimum right over here, not too far in, and there's the x. Once I do a calc minimum and go to the home screen and type x, it will be that value. Then I do y1 of x, that will be the y value. So there's the x and y coordinates, not of the minimum, but the same x and the y coordinate of the corresponding point on the original graph, which is going to be an inflection point. And I did that for every one of these max and mins on the derivative. And you can see those worked out there. So you should try some of those on your calculator yourself. If you need to, pause the video for a bit. Make sure you know how to do at least one or two of these to make sure you're going well. Okay, so here again, this is the original function in blue, the derivative in red, the second derivative in green. Here you can see maybe a little better picture of all of them. And here's just the original function, 2 periods. But notice I put in purple those places where the inflection points are. And you can see those worked out here with their locations. At least I did that for this period from 0 to 2 pi. And of course, there are infinitely many of those as well. If we wanted to put the full list, we'd need to shift those by 2 pi over 3. Okay, well, that was kind of involved. There was a lot of things that we got to review. We got to practice a lot of things, some of which were easy, some of which weren't quite so easy. But we noticed we were able to take this. We were able to use quite a bit of algebra. We talked about polynomials. We were able to talk about periodic functions with trig functions. We were able to talk about some of our special angles and solving trigonometric equations. We talked about factoring. We talked about special angles there. We talked about derivatives, first and second derivatives. We've got to talk about the chain rule there a bit. Some derivatives of trig functions, some trig identities, approximation techniques, using our calculators to do things, looking at graphs, and analyzing things. So lots of things that we could do. Notice between these purple points, it's all concave up from here to here. Between these two, it's all concave down. The original, between here and here, the original's concave up, and then concave down to here, and back up to here, and back down, and so forth. You just keep switching back and forth to concave up and concave down. So we have an interesting thing. So if you look at, this thing goes up higher here, comes back down to a low point, back up the axis, back down to the low point, back up to the high point, back down the axis, back to the high point, and so forth, and it just keeps going in this kind of a periodic manner. So that gives us an analysis of a trig function, and hopefully along the way we got to review some things that you needed to know from algebra and trigonometry, as well as derivatives and calculus.